Hello and welcome to this new video. Today we are going to talk about the Linux kernel 6.18, mitigation, VM change, and even a little bit of assembly coming up. Let's take a look at the note that Linus left us. Now there are three things that I want you to get away from this note. First thing, that there was some debugging very late in the release, a week before the release. Now this was not big enough for Linus to decide to push back the release, but it's still something big to note because it's not a fun thing. He also asked a little bit earlier into the release candidate to have everything ready at the merge window. So remember, when we release a kernel, the merge window open, which means that people can push their requests to the kernel. They can put their pull request and Linus can look at them to see if he decides to put them into the kernel. Now he asked everybody to be ready because of course the holidays are coming up, and who says holidays says absolute mayhem for managing a group of people. So of course, we need to have all of our ducks in a row and make sure that everything is done as fast and as correctly as possible, which is what Linus wants. Now, on the same subject, 6.19 could have some issues where we would need to push back a week the release. Of course, this is normally what we would do during the holidays, but Linus is still not sure that he wants to do it because the regular schedule will land us in February, and to borrow his word, people will have gotten over their food coma by then, which is the right way to say it. Let's get to the release. So let's get started with our first featured change of the day, which are sheaves. Now, sheaves are a new layer for caching objects via per CPU arrays. Now, to understand any of that, we need to understand a little bit about the history of how the kernel allocates small chunks of memory. So when we need small objects, we will usually call on slab. Now, slab can give you a smaller than a page object by taking one or more page, dividing it into smaller objects, and on request, we can take a slot from the slab to fulfill the allocation request. Now, this concept was created a long time ago by a guy called Bonwick. So Bonwick made it for Solaris, and it was implemented pretty much everywhere in the Unix world. Now, in Linux, there was multiple slab implementation. There was the original slab, there was slob for embedded device, and there was slob with a U, which is the latest implementation. Now, only one implementation remain, slob. So if ever you hear slab or slob, they're being used interchangeably because there's no other slab implementation than slob. So when slob was added to the kernel in 2007, or in 2.6.22, it brought a bunch of good features that people wanted. So it had NUMA policy support and a bunch of other things. It also increased performance by 5 or 10% and reduced by 50% the slab cache being used by the system. So slob was a big thing, but it still did not address all the issues of the slab implementation. So slab has this issue where there is a lot of contention around slabs whenever we have a lot of cores trying to request the same size of slab. Now, this was known for a long time. In fact, even Bonwick himself knew that this was an issue, so much so that he wrote a paper about it, describing a new concept that he called magazine. Now, when we're talking about magazines, Bonwick is an American. That means that we're talking about guns here. But, of course, this was a very bad name, so it was renamed Sheaves for Linux purposes. So let's just try to compare slab and sheaves for a moment. So whenever you use slabs, if you free an object, if you add an object, or if you need another slab, you might have to get a lock. So you might have to literally block the rest of your system for this specific type of objects. So this is, of course, not great. So how do we fix this? Now, sheaves do it by allowing us to do two things. The first thing that it will do is it will allow us to pre-allocate. So we can tell sheaves, so we're going on average to need this amount of objects, and at worst, we will need this specific amount. So by having those parameters, we're able to first give per CPU sheaves for the average amount of allocation, and then store additional sheaves inside of a barn for the worst case scenario. Now, just for those that are not English viewers, sheaves we're talking about a bundle of stalks, a bundle of plants, right? So when we think of a sheaves, we're taking like one straw out of the package of sheaves. That's the analogy, and that's why we're talking about barns. We're talking about taking the sheaves to the barn. Anyway, now you understand the analogy, but this is the idea. So having this pre-allocation and having this on CPU, this per CPU array, allows us to be way faster. Because on a standard, let's say you're trying to allocate a bunch of small chunks of memory, well, if we already know the average allocation that we're going to need, we can make sure that we have enough on the CPU for that. So most of the time it will be very fast. We won't have to wait for a lock or anything. And whenever we need to go over that, whenever we get into the worst case scenario, then we can take the lock where it will be stored inside of a barn that shouldn't be really that much used because the average scenario should not need that barn. Now, we're not getting into too deep of a specific with sheaves, but sheaves achieve this by, of course, keeping one sheave on the CPU and keeping a backup sheaves on the CPU, allowing us to have more than enough to process the average task and then being able to take more at the barn. So now knowing all of that, what does it mean for performance? Well, right now it's a little bit hard to know because if we blanket apply sheaves throughout the kernel, it will show us a bunch of performance gain, but also a bunch of regression. The big reason for that is that the step of pre-allocation can be long, and if it's not set correctly, it will yield big regression. It will cause a lot of issues. So for now, sheaves are an opt-in feature, but we will see probably more and more the implementation being done through the kernel at different parts, and it should yield pretty impressive performance increase. So let's get into the second change of the day, which is AMD SCV CipherText Hiding support. Now, we know I love AMD's SCV SNP, I love Intel's TDX, I love the idea of confidential computing. Now, there's been a lot of movement on that side and things have been going great. But today we're going down pretty much a not so good path. So let's go into a paper that is called Relocate Vote. So Relocate Vote was a paper made by a couple of Canadian universities. So it discovered a vulnerability in AMD's SCV SNP that allows a malicious hypervisor to extract some information from the ciphertext. So here, when we're talking about ciphertext, we're talking about the encrypted memory of the VM. So the way that encryption works for AMD, and it also works the same for Intel when we're talking about TDX or SCV SNP, is it will split the memory into 16 bytes chunk, and it will encrypt it using the key from the VM along with a tweak that is provided by the physical address. So what that means is if I encrypt, let's say 0 on physical address 1 and I encrypt 0 on physical address 2, it will give me different values. So if I were to read as the hypervisor those two values, it would show different results. So this is used so that you cannot just read the whole memory and then see what the prevalent values are to try to guess what the 0 is. Because if you know that zeros happen about 30% of the time in memory, you would be able to guess that the value that happens 30% of the time is 0. But this is of course not possible because of that address base tweak. Now, the issue here is that AMD and also Intel have this feature where you can move memory. So you can tell a specific page to move from one place to another. So you can probably see where the issue starts is that you can move different page to the same spot in memory and try at that point to guess what the 0 or the most prevalent value is. So using that technique, we can at least guess where the 0 is, because of course in Linux, the most prevalent value will pretty much always be 0. So you can guess what your 0 is. And after that, you can maybe start breaking some more complex things. So you can break the address space layout randomization. You can try to leak some positional information based on where there's zeros, where there's an actual value. So this is not good, right? This is not what we want. And this is empowered by two features. So the feature to be able to move pages of memory and the feature to be able to read that memory from the hypervisor's point of view. Now, on AMD, the hypervisor can read memory. On Intel, this is not the case. So this is why this is more of an AMD problem than a TDX issue. So the support of AMD SCVSNP CipherText Hiding is crucial in order to have more protection, because we wouldn't want the hypervisor to know where the zeros are. We wouldn't want the hypervisor to be able to guess maybe more values because they know they are more prevalent in some specific type of servers. So this is a very important thing to implement. So now AMD SNPs have this feature, and you will be able to enable it on the CPUs that have this feature. Because of course this needs to be enforced by the hardware, because if it were not, it would be easy to just trick the guest into saying that it is enforced. So it is great to see that feature. Now, I just want to talk a little bit more about how insane you can go with these techniques. So there's actually a thing that you can do as a host that is magical. That is the idea of removing the write permission on the guest's memory. So in the paper, they actually talk about the idea that you just remove the write permission to all of the memory of the guest, and then it will prompt you, it will tell you which page are being edited at what time. And you can then compare the state before and after to see what changed inside of the page. So you can get even more insight into what is being modified inside of the memory. So you can really go deep into, pretty much breaking the encryption if you go in deep enough. So it is very important that we have this feature and that it is being enforced. So I'm very happy to see support for it in this kernel. So still on the VM side of things, let's talk about KVM that now has support for the control flow enforcement technology. So this is a very good news, right? Because control flow enforcement technology, CET, is comprised of two features. So we have shadow stacks and we have indirect branch tracking. So both of those are used inside of a standard kernel in order to do control flow integrity. So what it allows us is to make sure that an attacker cannot redirect the control flow to an authorized target. So we cannot just take whatever's running into kernel mode and just go somewhere else and execute some code that would break things, right? That's not our goal, so we want to prevent that. CET is there for that. So if we go a little bit deeper, shadow stacks, the way that they work is by creating a copy of the stack. So whenever you start a new function inside of any executable, it will create a stack. And when you return from that function, it will take the address somewhere at the top of the stack and it will return to that address. Now, shadow stacks, by copying that stack, it will create a secure copy and we will be able to compare the return address in order to make sure that we're not getting duped. So this feature is implemented in both Intel and AMD and is now available for KVM. And if we look to IBT, so indirect branch tracking, that's another feature that requires a special end branch instruction at the target of an indirect branch. So when we're talking about an indirect branch, we're talking about the jump RAX instruction, for example, where we're trying to jump to somewhere that is pointed to by a register. So we take the value inside of the register and we go to that address. So to make sure that we're not going to somewhere that we're not supposed to, the end branch instruction needs to be at the destination, at the target. And if it's not, the CPU will generate an exception. Now, this is only implemented by Intel. And for those who just want to think about it a little bit more, there's a bit more of a heavy lifting that is being done by something like Fine IBT that will actually have some knowledge of what we're supposed to find more than just end branch at the destination. But in any case, Intel has that feature, AMD does not. So whenever you enable CET on KVM, it will only enable shadow stacks for AMD and both for Intel. So it is great to see that for VMs, even more security inside of KVM. So now let's go into our architecture change where we can talk about x86 Intel. More precisely, we will talk about retpolines. So we will talk about the dreaded return trampoline. Now we've talked a lot about Spectre as a class of attack. It's also called branch target injection, but let's just do a quick TLDR about how it works. So a modern CPU will attempt to read ahead of the current instruction and load or execute an instruction ahead of time. This is called speculation. So speculative execution could run into a direct branch, for example, a jump instruction with a fixed address, and load it. Or it could also run into an indirect branch, so for example, a jump RAX, and not having the address where to jump, because of course it's a register value. The speculative execution does not know where it's supposed to go because it doesn't keep track of everything, right? Or else it would be called the CPU itself. It would not be speculative. So we don't know where we're supposed to jump. What does the CPU do? It will speculate. So this is where the issue comes, because this speculation can be hijacked and it just should not be used inside of important parts of the kernel or pretty much anywhere in the kernel. So REPLines replace that jump RAX instruction. So they provide for a safe substitute by trapping the speculative execution into a loop. So this is why it's called a trampoline, right? It's jumping in place, preventing it from jumping to a dangerous destination. Now, if we go one step lower, it works by tricking another predictor. So it works by tricking the return stack buffer. So the RSB stores the return address of the function the speculator is currently in. So an important thing to know is that the CPU will not use the RSB to return while it is actually executing the code. It only does so while in speculative execution. For the real execution, the CPU will use the address written at the top of the stack. So let's just look at some assembly here to make it concrete. So let's just read this assembly as a non-speculative CPU. So we're just reading this as if we're executing for real. So we look at, first, we have a call A instruction. So call A is a direct branch because when it will be compiled, we will jump directly to a specific address that we already know. So we jump to A. After that, we have move RAX. So we will move the value inside of the RAX register, so where we want to jump to the stack return value. So we will push that to the top of our stack. And after that, we use the return to jump to the value that we just placed in the stack. So here, instead of using a jump, we are using a return command, right? So we are pretty much just replacing the return command. Now let's read this as the speculator. So we do call.a. It's a direct branch, so there's no speculation happening there. We just go directly to A. Then we see move RAX. The predictor will ignore this command because it has no ability to execute it correctly. After that, the speculator will see return. Now, not having the value at the top of the stack, it will just return to the value stored in the RSB. So, of course, the return stack buffer. So that value is right after our call A. So we go to .trap. After that, it will execute pause lfence, which pretty much does nothing. And after that, we have a jump.trap, which will push us back at the start of the trap into an infinite loop, essentially disabling speculation. So here, the REPLine disables speculation by making sure that the speculative execution does not get in contact with any indirect branch. So I just want to say real quick, big props to the source because they have some great writing on this. So go see the website, really great. Anyway, today, the reason why I want to talk about REPLines is because of an optimization that Intel did to FineIBT. So of course, FineIBT will use the REPLine. Not only that, but it will know if a REPLine is returning to a safe value, to a value it's supposed to. So knowing how the REPLine works, we now can take a quick look at the assembly that is used to implement it. So if we were to look inside of a compiled kernel, a REPLine would look like this. So CS call, x86, and all of the rest. So whenever we boot the kernel, this should be replaced to the value that fits whichever CPU we are running. Because if we are running an Intel CPU with FineIBT, it might be one set of commands, but if we are running a CPU that does not have FineIBT, for example, any AMD CPU, well, then we would not use these same values, the same code to run it. Now, the way that Linux does it is by punching a hole through the assembly. So right here, we would replace that CS call x86 by call R11 nope 3. Now, nope 3 here exists to keep alignment. Remember that assembly is something that is really important to keep a line because when we have jump instruction, if it's a direct branch, we are counting the address. We need to make sure that alignment is kept. So if we look at call R11, so this instruction is 2 byte wide, and then we have the nope 3, which is 3 byte wide, we fill the 5 byte wide hole that we created. Now the issue is that nope 3 actually takes one CPU cycle to execute, so it's not an instant thing, right? We are wasting time processing the nope 3 instruction. So how do we make sure that we don't have that nope 3 instruction that actually takes a CPU cycle? Well, we can use an optimization method called CS padding. So CS segment override prefix allows us to fill those missing bytes without wasting any cycle. Now the issue is that not all CPU can process the CS prefix without wasting cycles. Some Atom CPUs, so the efficiency cores of Intel, are worse than that, and it takes them longer to process CS than nope. So we need to find some kind of middle ground where we can allow some number of CS prefix, but over that we should really switch to a nope just to make sure that we minimize the tax on the ill-equipped CPU. So here the middle ground was 3 CS prefix. Over that we just use nope, which will be faster to process. So now let's go into Intel TDX, which now supports kexec. So kexecs are a mechanism that the kernel uses to load and boot a new kernel from a currently running one. So this allows us to skip the bootloading phase and the hardware initialization phase. So kexec did not work with TDX as the memory encryption hardware did not respect cache coherency. This is the ability, of course, to keep a consistent value along multiple cache. So because this wasn't kept, this would allow to write back old cache lines on top of the data in the new kernel. So we would write old data on new kernel, not a good idea. So the changes were made to make sure that this wouldn't be an issue, but kexec is still unable to boot a TDX kernel from a TDX kernel. So we can only boot a non-TDX kernel from TDX, not a still TDX-enabled kernel. So this is good. We have partial kexec support, but not total. So this fix works for most, but it doesn't apply to some early Intel Xeon Sapphire Rapid processor, were made in 2022, because there's a bug that prevents the fix from being effective. We also have a fix for Intel Xeon 6 PCIe performance issues. So in Xeon 6, they have an issue where if a PCI Express is bifurcated, so is split in a 2x format, so of course you probably know, but you have your PCIe, it could be 16x, it could be 8x, it could be 4x, it could be 2x. So we can divide the PCIe down into smaller speeds. So if it's split into a 2x, it becomes sensible to some of its configuration. So we will lose a lot of performance if we don't have a specific configuration. Now, the fix is to disallow the incorrect configuration, so it will force a correct one. Now, the fix config in question is disabling the extended tag. So extended tag allows a PCI device to handle more transactions at a time. So we go from 32 transactions to 256. It also disallows the 10-bit tag requester. So it's pretty much the same thing, but instead of 256 is 1024 transactions. We don't have support for that right now in the kernel. I know that there was some work being done on it in 2021, but turns out it was never merged. So we still don't have features for that, so it doesn't really matter. And also the max read request size, so the MRRS, which needs to be set at 0. So the size is 128 bytes. So we will now be disallowed from an incorrect configuration. Now let's jump over to AMD with the new AMD Versal True RNG driver that is used in the AMD Versal Adaptive SoC. So those SoCs are a weird mix of CPU and FPGA. So we're talking about a somewhat programmable silicon. So these chips are possible because of the acquisition of Xilinx. So Xilinx was acquired by AMD in 2022. They specialize in those types of chips. So they are used for networking, for AI. So we are going to see more and more of those types of chips, but they are weird kind of things. We don't see them every day. We also see error detection and correction drivers for the AMD VersalNet SoC. So we see a lot of work being done in those types of SoC. Now, maybe a little bit more interesting, along in the error detection and correction change, AMD has added multiple model to their Family 26 line, which gives us a quick look into the future for AMD. So we find code for a 16-channel memory CPU, which should allow more performance and capacity. Now, not a surprise, Intel came out a little bit later and say that they were to cancel their Diamond Rapid CPU with 8-channel memory. So we're leaving only the 16-channel option. So we're seeing that on the server side of things, the secret to a good CPU seems to be more channel, more RAM, and it's not really that surprising, right? AI requires a lot of RAM, and pretty much all the fads require more RAM. So now let's talk about a patch for the good old AMD Bulldozer. So for the young folks out there, back in the early 2010s, AMD was struggling bad. So they were behind in every way to Intel, they were bleeding out cash, and they decided to go for a full redesign, and they came out with the Bulldozer. Now, that was a failure. It took AMD to the brink of bankruptcy, but of course, we know that they struck gold with Ryzen and they had the big comeback story. But anyway, let's go back to Bulldozer, which came out in 2011. It was full of change. So we had some new instruction set that were added. We had ABM, we had XOP, we had FMA4, we had F16C. We had a lot of new instruction set within it. Now, those instructions were not really used. They were pretty much all dropped, nobody used them. So whenever in 6.16 we had the x86 native CPU option that was added, where we were able to compile a kernel using the native CPU instruction, it brought out a lot of those instructions inside of the kernel. So it meant that we would compile some instructions that we did not normally use. Now the issue is that they were not correctly implemented inside of the kernel. So we had this issue where you compile using native function, those functions are not correctly implemented, so your compilation would fail. So this was fixed, the support for decoding the instruction was added, and Bulldozer could compile again. Now let's go to Long Arch, which now supports the Long Sun security engine chip. Now this chip allows for offloading random number generation, so RNG. It allows also trusted platform modules, so TPM2, and a bunch of more features. So it's great to see Long Sun, of course, bolstering their architecture. Along with that, let's just take a look at RISC-V, which now support MIPS vendor extensions. Now, when I say MIPS, let me be precise, I'm not talking about MIPS as a CPU type, as an architecture. I'm talking about MIPS as a business, as a trademark. The reason why I'm saying that is we are not implementing some old MIPS commands, we are implementing specific instruction for the new RISC-V MIPS trademark P8700 CPU. So this is all this is. We're not bringing out some old MIPS instruction. It's just a new CPU that's getting more features. Now talking a bit more generically, we have some optimization to CPA flush. So CPA flush, the code that is used to flush the translation look-aside buffer as part of the change page attribute, will now use the flush kernel change function directly. This will allow CPA flush to have access to a bunch of optimized instruction like invalidate PGB or rare. So we've seen before, we have benchmarks. As soon as we implement those instructions, it makes things very great. So it's good to see that we are implementing that across the kernel. And this is something that we're going to see more and more, right? Because when we go down into those critical part of the kernel, they often will have some kind of specific instructions for specific cases, but we can use a little bit of a more generic function in order to take care of those things because those generic functions are more optimized. So now let's go into the attack vector control, which we added last release, that can now manage the VMscape mitigation. So remember, the attack vector control allows us to kind of manage our mitigation in one place where we can say, okay, I only want to protect guest to host attack or host to guest, or you can choose which type of breach you want to allow, I guess. So you can choose what type of things you want to protect against. So VMscape is another type of branch predictor issue. It is a guest to host attack vector, so it is now part of the AVC. Now let's go into cryptography, where we see another optimization using the new two-way interleaved SHA-256 hashing support. So SHA-256 is a serialized algorithm. So it works by processing 64 bytes block, and it requires a 30-bit output of the prior block. So we have that 32-bit output that we need to keep, and we process the 64-byte block, and then we go to another set of 64-byte blocks using the prior output. So modern CPUs have the capability of processing multiple hash at once in parallel, but there's no way for us to apply multiple execution units to one single hash. So the optimization here comes from recognizing that we might have more than one hash to process and to feed the execution unit with a second hash while waiting for the first one to finish. So this optimization yields a throughput gain of about 98% on x86 and 70% on ARM. Now, those are the best numbers, of course, but it's kind of a crazy optimization when we think about it. So it is currently only applied to FS Verity, so it's a feature that checks the integrity of a read-only file, and a patch for DM Verity, which is pretty much the same thing at the block device level, is scheduled for next release. Now, wink wink, very important to note, the patch only extends to 2 execution units, but some CPUs have more. So that means that we may see in the future, if let's say we have 8 execution units for hash, we could see way more optimization coming down the line by using all 8 of them. So we'll see where this goes. It's going to be interesting. Now let's go into VM changes where, well, we've talked a lot about VM change, but we're going to talk about even more VM change for the support for AMD Secure AVIC. Now, before even getting into the new feature, let's understand a bit about how interrupts are handled in the CPU. So for a long time, CPUs have used X2 APIC to store and manage interrupts. So here, APIC means Advanced Programmable Interrupt Controller. So this is true for VM as well, where the host will emulate an X2 APIC for its guest. Now this is, of course, very slow, so AMD created an Advanced Virtual Interrupt Controller, AVIC, which brings the hardware acceleration to the VM. Now, that's fairly new too, so KVM now enables AVIC by default for Zen 4 and newer. This is new for this release, and it's still getting some more work. Now, Secure AVIC seeks to be the next evolution by providing a solution for confidential VM in line with AMD's expansion of features linked to the secured encrypted virtualization. So a Secure AVIC instance is owned and managed by the guest, which prevents a lot of possible attack pathways, so we don't have to worry about interrupt injection while still being hardware accelerated. Now, if you want to know more about it, there is a great Linux Plumber conference about it. I'll leave the notes in the comments and you'll be able to find it. It was done in 2023, so it's a long problem. It's a problem that we've had for some time, but I'm happy to see that it's been fixed. Now, while we're talking about SEV-SNP, we can talk about Secure TSC support. Now, if it sounds familiar, it's because we've covered it in 6.14, but it was ultimately removed from the final release. So a quick refresher. So Secure TSC removes the ability of the hypervisor to mess with the timestamp counter. So the timestamp counter, normally the hypervisor could mess with the frequency, could do a bunch of things that could lead to some attacks on the VM. Of course, Secure TSC disallows that and makes sure that the guest has full control of the timestamp counter. We also have detection of FreeBSD's Beehive hypervisor. So Beehive detection used to be only useful for printing hypervisor detected Beehive at boot time, but now Beehive rolls out support for more than 255 vCPUs, and detecting the 15-bit MSI is needed to have proper support. So it's good to see that we have that support. And while we're talking about 255 55 vCPUs or more, there was a bug affecting AMD's EPYC Genoa when using KVM and QEMU guests that was fixed. So this bug would misread the topology information when you have more than 255 vCPUs, and the fix was to enforce that the right topology information would be given to the guest. Now for the RISC-V side of things on KVM, we see support for the SBI FWFT extension, ZigBop, and bfloat16 extensions for guest VMs. Now we covered all of those instructions in 6.16, so if you want to know more about it, you know where to look for it. So our last feature for VM, we have Virtual Function I/O, so VFIO, that was saved from removal. So there was two devs that took up the role of maintainers for the VFIO platform driver. So this was something that was talked about in the past, about how the VFIO driver was not supported correctly and that nobody was taking care of it. If you want to know a little bit about why we would use the VFIO driver for anything, it is what you use when you want to do a GPU pass-through. So if you've ever done a GPU pass-through on Linux, well, I don't know in which case you would do it for another operating system or kernel, but if you have ever done a GPU pass-through, it was with VFIO. So along with some fix, we've added the support for the NVIDIA GB300. So we now have maintainer for VFIO. We should be good to go for some time. Now on the graphics side of things, I wanted to highlight one specific driver, Tier. Now Tier is a driver for the ARM Mali GPUs that eventually aims to replace the Panther driver. Now this is a Rust driver, so we're getting into spooky territory here. So the code that was added to the kernel is only a skeleton, but the devs behind it managed to run GNOME and SuperTuxCart on a testing build, so it seems that we're getting things along just fine. Now the reason why I'm excited about it is because once we have one full implementation of a driver inside of the Linux kernel, that means that it will be exponentially easier for others to do the same thing. So having all the pathways, the abstraction, having somebody that has done it before should allow us to have more hardware compatible under a Rust driver. So it's great to see the work that's getting put into it, even if I know that a bunch of people are going to be angry because Panther already exists. Now let's go into the file system change where bcachefs has been removed from the kernel. Yep, no bcachefs, should be the last time we talk about it. Now let's go to btrfs where we have a fix for a weird situation. So let's say that you have a C group, so you have a control group that is reading a lot of data on btrfs with a working set that is much larger than the memory limit. So you have way more things to read, way more things to store in memory than the amount of memory that you have. And you have a second C group that is trying to write some files along in the file system. We might have an issue where the first C groups will take some read locks and waste the time of the second C group, preventing it from performing the writes. So this was solved by making the reads take the lock of a prior transaction. So if you have a prior transaction where the extent of the data that you're trying to read have not changed, you should be able to read the prior transaction instead of the current one, allowing for a write to come true on that current one, but still being able to get your data and to pretty much abuse btrfs on the prior transaction. So this should fix the issue where the first C group was holding up everything because it would come in and out of memory, holding locks, and letting the second group actually write the files. We also have initial support for block size being greater than the kernel page size. So this is still experimental, so I'm not going to get into it that much because we don't have a lot of feature. We don't have RAID 5, we don't have RAID 6, no direct I/O, and a bunch of other things that are disabled when you enable this feature. So it is a good thing that we will probably cover way deeper in a future kernel whenever it gets stable. Now let's go to XFS where the online FSCK, so file system check, is now enabled by default. So after a year of this option existing, the XFS devs think it's stable enough in order to enable by default. So just a quick remember, online FSCK, what this means is we are able to repair the file system while running on it. So if it's mounted, if you're running things on your file system, you should be able to check the file system while it's running. So this is a feature that exists for a bunch of other FS, but it was still missing as a default on XFS. Now on SquashFS, we have a crazy optimization. I don't think that I've covered SquashFS before. So SquashFS is a compressed read-only file system, so it's used to make images and to boot from. So SquashFS has this optimization where they pretty much enabled sparse file. So if you don't know, you can copy over data using CP or using any other command using sparse file. The way that it will do that is it will read the file, and if ever it sees a big hole of zeros, instead of just throwing zeros, it will just say there is a hole there and it's full of zeros. So this should allow you to save a bunch of place if you have, for example, a big 15 gig files with 4 gig of zeros, right? So normally this function would be very slow on SquashFS because it wasn't fully implemented. So it would leave CP to just read all the data and try to find the zeros. But in reality, SquashFS, because it's compressed, has some ways to be able to know where the zeros are and has some ways to be able to see rapidly where we can actually find the holes. So this was implemented, this led up to a 150 performance increase, but in reality, it's pretty much comparing a feature that did not exist with something that actually implemented the feature, so good for SquashFS. Now moving over on F2FS, that now enforces a hash-only lookup by default. So this should speed up a lot of search on F2FS. So whenever you try to look into a directory, it will use hashes, which of course are faster. And we also have a new mount option to go with it where you can disable the hash-only lookup or enable some other mode. Now, along with that change, we saw a fix to checkpoints, which had an issue where they could lead to a couple of seconds of pause, so this was fixed. And we also have some read ahead in node blocks when you are in F2FS get block pre-cache mode. So this should allow for a performance increase. Now moving to XFAT, we see an optimization of the allocation bitmap loading time. So when a small cluster size was used with a large partition, it would result in a very long loading time for the allocation bitmap. Now, the solution to this was pretty simple. It was the implementation of a read ahead that yielded a 16x performance gain. So of course, trying to yield one cluster at a time when you have a large partition is probably not the way to go. Now on OverlayFS, we see that we have case-insensitive support. Now, this is not on a per directory basis like some other file system. It is only for the whole file system or for nothing. Now, I think what's the funniest thing that I could see from that is the comments on Phoronix's website. People really hate the idea of something being case insensitive, and it's just really funny to see how people react to it. Now, even if it's nothing big, I still want to talk about HFS a little bit. So last release, we talked about HFS having some new maintainers, and we still have some more small fixes. So things are going ahead well on that side. We will see HFS survive. It's not as if we only saw one release and then the maintainer go into hiding. So it's fun to see. So this release, we have a new device mapper. So we have DM Bcache. Now, it aims to be used in front of slower block device by providing a high throughput, low latency cache. Now, when we compare it to other options in the kernel like Bcache, like when I say Bcache, I'm not talking about Bcachefs, but really original Bcache and DM write cache, we can see that it has an higher throughput than Bcache while maintaining the low latency of DM write cache. So it gives some huge improvement without needing to reformat. So we have really a drop in replacement, which is great to see. Maple time, this is maple time. Yes, you are at the end of the video. You have the right to have the word to show that you are an absolute unit, which is Sheaves. So let's start by the beginning, okay? Because I know that there's going to be 4,000 comments about it. Yes, okay, the pop filter, pop, has been added to the shopping carts. So that's kind of necessary with the mic in that format. Okay, so Last video, my outro was cut out very rudely by my bad editing, so let's just go into TLDR of what I want to say, just in case I manage to mess up again. So, more videos to come, way earlier, but bad quality videos. Okay, we're doing devlog, like the trashiest vlog ever. That's where we're going. Okay, because I have a lot of projects. I need to focus on them, and because if I don't, I'm not going to do anything. I'm like getting crazy over here, speaking at the walls, being like, I need to do more SQL and Python. Okay, this is why I live. So we're going to make some SQL and Python together in the future projects that I will make some videos about. But no high quality stuff for some time. Well, only the kernel videos, but I'm going to be honest here. The last kernel videos have not been up to what I want them to be, but it's kind of a time thing, so I don't have enough time to make my great vision of what I want it to be. So, yeah, we're going to have to work on that, but the projects that I'm working on should fix a little bit of that. So in any case, I'll stay mysterious a bit. If you are only here for the kernel videos, thank you for supporting me. We won't see each other, for this year, because this is the last kernel of the year. So, of course, if you did enjoy the kernel, I'm very happy about it. Thank you for supporting me. Happy New Year, happy festivities. For all of the other people that are willing to watch me vomit some Python and SQL, oh boy, are you in for a treat. We're seeing each other soon. Take care.